Good morning, everyone. So I thought we'd talk a little bit about midterm 4. So I was mentioning the average last time is in the range of about 65%. I think it's closer to probably 64%. Somehow that's about 5% better than the other classes, so that's good at least. So we at least beat the other class. Overall, maybe not entirely where we would have wanted you guys would have wanted your exam scores to be. Hopefully they'll be released later today so you can get a chance to see it. I think there are plenty of scores that were, I think a lot of you guys will be happy with your score. If you're not happy with your score, I would just think ways of, better trying to learn the content kind of slowly by reviewing the chapter, kind of reviewing the examples in the chapter, understanding those core ideas. A lot of those ideas, a lot of the questions that are embedded within the chapters end up being the basis of a lot of our exam questions. But overall, I wanted to think about kind of where grades are tracking at the moment. Our overall exam average is about 67% if you take the average of all of the 4 midterms. You might think on the 4 collective exams, how have you done? I think it's not uncommon for a student to have done not so great on one of them, but much better on the other 3. So if you're in that category, hopefully your scores in a higher range. The homework lab recitation average is like 91%. So when you look at the overall score for the class, the overall average is about 77%. That would fall into the B- range. So I think grades are tracking towards like a B- average. If the final exam score happens to tick up a little bit, I think the average could tick even higher, and that's great. So I think make sure to go to the last couple recitations. This coming Tuesday's recitation is a review activity. The final recitation activities, a chapter 10 and 11 review packet, and then we'll have some practice materials for the final. We'll do some review here in class, and so hopefully we're well situated to do well in the final exam. So with that, I just want to give a reminder that Monday's class is canceled, lectures canceled, office hours are canceled. So hopefully you guys, who's planning to go somewhere for the eclipse, anybody actually going to try to get into totality? All right, good luck. Hopefully, good luck with the weather, really. So right now it's like, will there be the ability to see the sun, hopefully. But anyways, so getting back into the material here. So we're talking about the ideal gas law. We have PV is equal to nRT. And then we have a few ideas from last time that we're trying to use that the moles is the mass of a sample divided by its molar mass. And then we could plug that into the equation here. We have pressure volume mass over molar mass times RT. And so then you can have a given amount of mass that's in a container at a certain temperature where the container has a certain volume. And we can relate the pressure, volume, mass, molar mass to temperature. And then we could also relate density because that's mass over volume. So if we rearrange our equation to have m over v, we divide both sides by volume, then volume's over here. And if we divide or multiply both sides by the molar mass, and molar mass is over here. And then we can have that the density here, so density is mass over volume, that's going to equal pressure times molar mass divided by RT. So you could relate pressure molar mass to the ideal gas constant and then the temperature of the gas. And then our ideal gas constant, the one that we're going to use the most, so if we get used to this number here, 0.08206, that's liter ATM per mole Kelvin. And so let's say we have a certain quantity of CH4 in a vessel at 2.50 liter vessel at 23 degrees C. Can we calculate the pressure of the gas sample? So for this problem here, I could do this in kind of one of 2 ways. I could just try to calculate the number of moles using the molar mass of CH4, or I could just use the m over molar mass expression that we wrote. So if I'm trying to use this expression here, I can take my pressure times volume is equal to m over molar mass times RT. And I'm solving for pressure, so let's divide by volume. So we'll divide by volume. And so then we can calculate for the pressure. So pressure should be the mass, 7.50 grams, times the ideal gas constant, You guys might expect the easiest way to make a mistake is to probably just leave the units off. I see a lot of times, very common for you guys to not want to write the units, but just write the units in because they'll help us catch mistakes and make sure that our units work out correctly. And then we have times the temperature. We have to go to Kelvin because our temperature is in Kelvin, so 23 degrees C plus 273.15 Kelvin to convert to Kelvin. So that converts us over to Kelvin. And so let's actually just do that part of the calculation right off the bat. So let's just do 23, should be 296. Just making sure, yep, so 296 Kelvin. And then we're going to divide this by the molar mass of CH4. So the molar mass of CH4 is just taking carbon plus 4 hydrogens. And so the molar mass of CH4 is work it out more precisely, so 12.01 plus 1.008 times 4, that's 16.04 grams per mole. So we'll divide by that here. And then we throw in the volume of the container, 2.50 liters. And so let's work out the units to show how everything's canceling here. So we have our Kelvin canceling here. We have the grams canceling here. We have liters divided by liters, so that cancels. And then we have the denominator has 1 over moles. We flip that up to, so when I flip this up to here, this would be moles on top, so that cancels out with the moles there. And everything is canceled except for atmospheres. So this is how we can calculate the pressure of that gas in ATM. And then we can convert it over to torr afterwards. So we calculate this quantity here, 7.5 times 0.08206 times 296, divide by 16.04, divide by 2.5. I get 4.54 atmospheres. And then 1 ATM, if we want to convert this, because it asks us to convert this into torr as well. So the pressure in ATM, 4.54 ATM, multiply by 760 to go to torr. So that would be 3,450 torr. So we're just using 1 ATM equal to 760 torr. So things that are usually a given, like ideal gas law is usually on the test, but I mean, hopefully that's an equation that once we use it a few times is easy to remember. We'll give you the ideal gas constant in liter atmospheres per mole Kelvin. So you'll have the ideal gas constant on the test. And then we'll give you the pressure conversions. We'll give you the conversion from ATM to torr. So there's not a lot of memorization per se going on, though I think most of these conversion factors for degree C to Kelvin, that's also given on the test. That's been given on the test since midterm 1. But a lot of them we will come to know, hopefully, and not have to look up every time we need to use them. And so then the next question asks, well, what's the density of this gas sample? And there's a few different ways of thinking of the density of the gas sample. One way would be, well, we can go back to this expression here. So let's think of 2 ways to solve for the density. One way would be, well, we just wrote this equation that we have density is the pressure times the molar mass divided by RT. And so we have the pressure here. And so we're going to choose the pressure probably in ATM because we'll want to use the ideal gas constant with units of atmospheres. So if we take the 4.54 ATM that we calculated, we take the molar mass of CH4, 16.04 grams per mole, and then we divide by RT. So 0.08206 liter atmospheres per mole Kelvin. and then times the temperature, we were at 296 Kelvin. So for this method, again, we're just taking the pressure times the molar mass. I should show the units canceling. We'll do that after we work out the math. I get 3.00 grams per milliliter, or grams per liter. And let's work the units out real quick. Our atmospheres cancel. The 1 over mole flips up to cancel with the per mole. The Kelvin cancels. And the only units not canceling are grams per liter. So that's how we get the unit out in grams per liter. So that's how we know the unit here is in grams per liter, and it wasn't in grams per milliliter or some other unit. It's through the cancellation of the units. And so 3 grams per liter is the density of this gas sample. Now, what's another way we could calculate the density? Was anybody thinking that there was a simpler way to calculate the density? Like if you're looking at the initial problem where we were looking at a gas sample, 7.50 grams of a sample in a 2.5 liter vessel, that's the density right there too. So we can just go back that density. So a second way to calculate density here would have been just to recognize its mass over volume. And we had the mass of the sample was 7.50 grams and was put into a 2.50 liter vessel. And so that would give us 3.00 grams per liter. So 2 ways we can get to that particular density, and 2 ways we can think about it. It's still mass over volume. If we had the mass and the volume, we could solve for it. We can also relate density to pressure and temperature and the molar mass of the gas from the ideal gas law. As I'm sitting here, I'm thinking there's like, I think this problem's pretty easy. Hopefully you see this is pretty easy. Like a complicated question that kind of goes back to some gas law questions would be, well, what if this gas sample were to expand and change its pressure and change its temperature? And then the volume would change accordingly. And so we might ask a question like what would the volume of this gas be if it were to expand to STP? So the gas sample pressure is at a higher pressure, and so if we let that pressure expand, so we lower the pressure, so to lower the pressure we're going to expand the volume. So we saw in the idea of pressure versus volume from, what was that, Boyle's law, was that if you decrease the volume, you increase the pressure. Well, if you increase the volume, you decrease the pressure. And we can also change the temperature. And this also gives me a chance just to give you the reminder that, and I don't know why sometimes we focus on this so much on tests, that STP is 0 degrees C and 1 ATM. So it's precisely 0 degrees C and 1 ATM, not 25 degrees C. You would think it's 25 degrees C, but it's 0 degrees C. And then this also allows us to think that the quantity isn't changing. When I'm thinking of the ideal gas law, if I just go back to PV is equal to nRT, that the moles of gas is not what's changing here. So we're not changing how much quantity of gas there is in the sample. We're just changing the pressure and the volume and the temperature. And so if we think of how we could write PV over T is equal to NR, and then NR is equal to a constant, and then that's not changing, that would allow us to write that P1 V1 over T1 is equal to P2 V2 over T2. Because P1 V1 over T1 is equal to NR. NR is not changing, so there's no N1 versus N2, because N1 is N2. N1 is constant. R is the ideal gas constant, so it's by definition a constant. And so the idea here is that P1 V1 over T1 is equal to NR, and then P2 V2 over T2 is also equal to NR. So if they're both equal to the same NR, then they have to be equal to each other. So that's how we can write expressions that look like this. And then it just becomes a matter of if we're trying to solve for V2, so we're trying to solve for the new V2 given a temperature change and a pressure change. And so if we were to write that V2, the new volume, should be equal to P1 V1 over T1, and then times T2, and then divide by P2. So I'm just doing the cross multiplication to solve for V2. Okay, so this is a pressure volume change or a pressure volume and temperature change of a gas sample where we can calculate the new volume of the gas sample. So our V2 would be equal to plugging in the initial pressure. That was 4.54 atm, the pressure we calculated in the first step. The initial volume was 2.50 liters. The initial temperature, if you recall, was 296 Kelvin. And we just multiply by the new temperature, 273 Kelvin. If you want to be technical, 273.15 Kelvin, because the STP is precisely 0 degrees C, so exactly 0 degrees C. So that's 273.15 Kelvin. And then we divide by the new pressure. The new pressure is exactly 1 atm. So we're exactly at that temperature and exactly at that pressure when we're at STP. So again, those are what it means to be at standard temperature and pressure. And so we just do the math. And again, we'd probably expect this volume to expand. And it does. So my V2 works out to be 10.5 liters. So I think you can imagine like a gas cylinder or something that holds a gas at a high pressure. And I think you can imagine that gas expanding. Maybe it fills a balloon or something. So maybe we take a gas cylinder and we empty it and we fill up a balloon, and the balloon happens to be at 0 degrees C, and the balloon's just going to fill up to room pressure. So most balloons are just at the pressure of the room. And so if that's the case, this balloon should fill up to about 10.5 liters with the gas that we would have had contained in the initial sample. Okay, so this is just like an example of kind of like a gas law problem where we can change one of the pressure variables using the ideal gas law. Okay, so in some ways, pressure expansion and contraction, I mean, that's not exactly chemistry. To me, that's physics. You know, there's not a chemical reaction taking place when we're changing pressure and changing volume. But what if we have a chemical reaction take place that generates a gas? And so we can generate gas from chemical reactions. So how many grams of this sodium azide? Sodium azide used to be used in airbags. It might be used in some airbags still, and maybe in place in older cars. But it's one of the first reactions that was used to be able to generate a gas on demand. So what happens is if you heat up the sodium azide, it decomposes into sodium metal and N2 gas. And then this heat source, you can have that provided on impact. So you have an impact take place when there's an impact of a car that could lead there to be a heat source that's applied to the sodium azide. Then it heats it up where it leads to this decomposition reaction where it leads to N2. We talked about this as an example of decomposition reaction back in chapter 3 when we were starting to talk about chemical reactions. But the key here is that you have a solid that can generate a gas. That gas can then fill an airbag. Now, the reason why this probably isn't the most widely used compound in automobiles anymore is that the sodium metal would often fly out with the N2, and sodium metal will react with just about anything, right? Because we saw it dissolve in water very readily, so it dissolves in the airbag material, burns the airbag, burns the driver. So maybe you survive the car crash, but then you get a chemical burn from the sodium metal from this reaction. So these days, most airbags in a car are generally just filled up with like a CO2 pack that's just designed to release the gas that's stored in it in like an expansion process that we were kind of just talking about. But here, this question's asking how many grams of this compound here, the sodium, the NaN3, must be decomposed in order to fill an airbag to 50 liters with 1.25 atmospheres of N2 at 22 degrees C by this reaction. So the key is that the airbag's filling with N2. So when I think of PV is equal to nRT, that this is the N2, because that's the gas. And so the gas fills the airbag. The gas is made up of the N2 molecules. And so if I calculate the moles of N2, I could calculate that by the pressure and the volume I need that balloon or the airbag to be filled to, and then divide by RT. And so I can take the pressure. I want the airbag to go to 1.25 ATM. It has to be 50 liters to completely fill the airbag. And then we're dividing by the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin. And then 22 plus 273, that's 295 Kelvin. So Kelvin cancels, liter cancels, ATM cancels. Everything's canceling except in the denominator 1 over moles, which flips up to give us moles. So we do 1.25 times 50 liters, divide by the gas constant. So I get 2.58 moles are required to fill that airbag to that particular volume at that temperature. But the question isn't asking how much N2 do we need, it's asking how much of the NaN3 do we need to produce this N2. So do you see how this kind of becomes a stoichiometry problem? It becomes a question of, well, to get to this quantity, how many grams of the NaN3 are required? So it takes us back to chapter 3. So if we just think of how we used to solve, or how we would solve a stoichiometry problem, let's just use dimensional analysis. So let's just think, if we want to produce 2.58 moles of N2, we know for every 3 moles of N2 that are produced by this reaction, we needed to have decomposed 2 moles of the NaN3. So just every 3 moles of N2 that are produced means that there had to initially be 2 moles of NaN3 to decompose, and then 1 mole, which is use the molar mass of NaN3. So it should be 23.00 for sodium, plus 14.01 times 3. That's 65.03 grams. So I get 112 grams. So again, the idea of this problem is we're taking a chemical reaction where we have a solid producing another solid, but a gas. The gas is filling the airbag. We figure out how much gas is in the airbag. We relate that back to how much of the starting NaN3 had to initially been present to decompose. So then, the kind of middle part of this chapter 10 gets into mixtures of gases. And mixtures of gases are important because, like, we breathe one of the gas mixtures in of air. So air, I don't know if, I think probably everyone knows what air is, right? What it's comprised of, or at least, I don't know if you guys know the specific percentages, but by volume, the composition of air is about 78% N2, about 21% O2. I think we talked about this before, that the next most abundant component, do you guys remember what it is? Anybody remember? It's argon, is actually about 1%. And then everything else is the remaining, like, less than 1%. Or if you actually add up the percentages, it's like less than a percent, less than 0.01% is everything else, like your water vapor, your CO2, other volatile organic components of the atmosphere, other substances. So these are the major components of air. And so we're always breathing in a gas mixture. So let's talk about gas mixtures. So if we think of the ideal gas law, gas mixtures, we wouldn't expect them to react with each other. That's why we can have O2 and N2 together, is because they might bump into each other, but they're not reacting together. If they did, they probably would have reacted by now. And so two gases that do not react in a combined container, they act as if they're alone. So the sort of pressure of N2 in air has the pressure it would have as if there were no O2 or argon or anything else present. And the same thing with the O2. The pressure of O2 in air would be the pressure it would have if there was nothing else present in air. So if I take the total pressure of a gas mixture, the total pressure of a gas mixture is just the sum of the partial pressures of each of the components of the gas mixture. And so since air, if we assume that this is 1 atm, that's standard atmospheric pressure, and so if 0.78% of the volume is N2, then 0.78% of the pressure would be N2. And so the partial pressure, so at 1 atm, we'd have a partial pressure of N2 that would be equal to 0.78 atm. The partial pressure of O2 would be equal to 0.21 atmospheres, and the partial pressure of argon would be equal to 0.01 atm. That's just those fractions of the volume. Because we're at 1 atm total, that if you add up all of these pressures would add up to 1 atm. And so the sum of the components of the gas mixture add up to the total pressure. Now, if you're thinking, okay, it looks like there's some ratio of the component compared to the total, can we relate that to maybe like the moles of the components in the mixture? So let's think about how we can compare like the total pressure to the total number of moles. And so what this slide here is comparing is that if you think of the partial pressure of component 1, so if you're thinking PV is equal to nRT, and you're thinking of the component 1, that's just going to correspond to the moles of the component 1. And then you can write that the partial pressure of component 1 is pressure, the pressure of component 1 is just N, the moles of component 1 times RT divided by V. The temperature and the volume of a gas sample are the same. Like if we have oxygen in a gas sample, N2 in a gas sample, they have the same temperature and they occupy the same total volume. So they're in the same container, so they have the same temperature and volume as each other. So if we think of the total pressure, again, the total pressure would just relate to the volume times the total number of moles times RT. So the total pressure is just equal to the total number of moles times RT divided by V. And then RT and V are the same as each other. They're constants. So the temperature of component 1 is the same as the temperature of component 2. So they cancel into each other. And that simplifies down the partial pressure of component 1 divided by the total pressure is just equal to the moles of component 1 divided by the total number of moles. And this total here, N1 over NT, is what we call the mole fraction of component 1. So the mole fraction of component 1 is just the moles of component 1 divided by the total number of moles. And so this here is just what we call a mole fraction. So the ratio of the moles of a substance to the total moles is that mole fraction. It's the symbol X, like looks like chi here, but I think we symbolize it with the symbol X. And so the moles of component 1 divided by the total moles is that is the mole fraction. And so then if we just do a little bit of math here, you can see that if the mole fraction of 1 is equal to the partial pressure of 1 divided by the total pressure, then the partial pressure component 1 is the mole fraction of 1 times the total pressure. So just doing a rearrange on this equation here leads to this equation here. So the partial pressure of one component is just its mole fraction times the total pressure. So not a derivation you'll probably ever have to work through, but this here is Dalton's law of partial pressures, that you can relate the partial pressure of a component to its mole fraction times the total number of moles. And so we can calculate total pressures of gas mixtures and try to relate maybe the partial pressures of the two components. So when we see a problem like this, it's asking us to calculate the total pressure in atmospheres of a mixture of gases. We have helium and oxygen, so we wouldn't expect helium and oxygen to react together. And so we get a gas mixture here of non-interacting gas particles in a 15-liter vessel, 298 Kelvin. So the two ways I can think to solve this problem would be to calculate the total pressure by taking N total times RT divided by V. And I would just have to calculate the moles of helium, the moles of oxygen, add them up together, and then sum them together, and I can solve in this equation here. Or I could think of calculating the partial pressure of the helium in the mixture by taking the moles of helium times RT divided by V. And then I could add that to the partial pressure of O2 by taking the moles of O2 times RT divided by the volume. To me, like doing it the longer way may make sense to do it once, where if you just think of taking and calculating the partial pressure of helium, where we would take the 5.0 grams of helium divide by it's the mass over the molar mass, but let me think of writing it slightly differently. Let me write the 5.00 grams and then do the math this way, where I go 4.003 for helium. That's per mole of helium. Just so that I can see that I'm calculating moles here. So then I can multiply by RT. And then I need to divide by the volume of the container, 15 liters. So 5.00 divided by 4.003, that's the moles of helium. In fact, I'm going to write that up here too, because the moles of helium, I got 1.25 moles of helium. So I can kind of run through this two different ways and show you two different approaches to solving this problem. So that's the moles of helium, but then I'm just taking that times RT. And then dividing by 15 liters. So that gives me 2.04 ATM. So that's our partial pressure of helium. Our partial pressure of oxygen is the moles of oxygen. I have 5 grams of oxygen as well. O2's molar mass is 32.00. If you force yourself to write the gas constant a few times, I don't think you're ever going to forget it, or at least not for a while. So that's why I'm kind of taking the time to just write it, not just writing R and assuming that we remember what it is. But then we can also see how the units cancel, how the mole cancels, how the Kelvin cancels, and then the liter cancels, and I get units of ATM. So I can make sure that the units cancel too whenever I take the time to write the units in. And so I get my partial pressure of oxygen. So when I go 5 divided by 32.00, that's the moles. If I hit enter, that's the moles of oxygen. So I'll just save that up top so I can run through the second approach to see that either way gives us the same pressure. But to cap off, so 5 divided by 32 times the gas constant, 0.08206, times 298, divided by 15. I get 0.255. So now my total pressure should be the sum of the helium plus the sum of the oxygen partial pressures. So that's just the 2.04 plus the 0.255 ATM values, and that should give me a pressure .29. So that's good. That looks like choice D. So again, the partial pressure of helium, it exists as if the oxygen's not there. So we can just calculate the helium pressure. Then we can calculate the oxygen pressure as if the helium's not there, and calculate the partial pressure of oxygen. Then the total pressure is just those two values added together. I could also have just taken, and again, this is probably a quicker way to solve the problem. So if I take this as approach 1 and this is approach 2, approach 1's quicker, but maybe it doesn't necessarily make sense if we just had done this as the only way to solve the problem or had done it first. But we're just taking this times RT. So here I'll just write times RT. We know that's 0.08206 times 298 Kelvin. And then we're dividing this by 15 liters. So I take the sum of the moles. So it's 1.406. It's my total number of moles times 0.08206 times 298 divided by 15 liters, and I get 2.29 ATM. Like this chapter in particular is one where there's going to be 2 or 3 different ways that will get you to the same answer. Some of them may take more steps than others, and as long as you get the right answer, I don't think it matters too much which way you go. But if you can think through a lot of problems more than one way, I think we understand a concept. If you can think I can just add the 2 partial pressures together, that's one way to calculate the values, to calculate the total pressure. Or if you said I can just calculate the total moles and relate that to the total pressure. So that would work as well. So there's a technique, I think this is what we do still in the lab, where you have a bulb called a Dumas bulb. And so you have this bulb that has, it's just basically like a volumetric flask that you can fill with a liquid. When you do this experiment, you usually fill the whole thing with water to determine the volume of your vessel. So you fill it completely with water and you figure out how much mass of water was in there, and from the mass of water you work out the volume of water. And so then the second part of the experiment is once you determine the volume of the vessel, so we're just told the volume of the vessel here is this volume here, so we had that furnished to us. It's 355.3 cubic centimeters, that's just a milliliter of course. And so we have a bulb with units of milliliters, and then the second thing you can do is then fill this bulb with just a relatively small amount of a compound that has a boiling point near that of water. And so you fill it with like some sort of a substance. Imagine we put a little bit of substance in here, and then we allow that substance to vaporize in the water bath completely. So we sit there and we watch the sample come to a boil, and then the vapor inside the cell initially is air. So initially you have that gas cell filled with air, but as the sample heats up, some of the air flows out because of when temperature increases, we're going to have some of that air escape to keep a constant pressure. And then the other thing that's going to happen is when the sample starts to vaporize, it's going to take over the gas particles that actually fill the container. So when the sample vaporizes, we then have those particles kick the air out of the vessel, so the only gaseous particles left in the container are mostly from the compound that just vaporized. So it's a way that we can have this entire cell, we submerge it in the water bath, so that the entire cell is just filled up with the vapors of the compound. And so the thing that you're watching for is for the last drop to vaporize. So you go to complete vaporization, there's no liquid present inside the cell. And so then at that point, you can take the cell out of the water bath and then let it cool down. And so when it cools down, you can start to see the gaseous particles that were hot because the water in the bath here is boiling. So the sample's in a boiling water bath, you take it out, the gas cools and then recondenses. And so you can see, a lot less of the samples present now. Most of the sample that had vaporized left the cell, but then you're left behind with that atmospheric pressure. So the cell maintains a pressure at atmospheric pressure because it's open to the atmosphere. So once that pressure cools, you're then left with the liquid sample that you can get a mass of. And so the way you start this experiment, you have a clean bulb, you fill it with a liquid, you then mass the bulb after all the liquid vaporizes at 100 degrees C, and then you allow that tube to cool so you can put it on a balance to get the mass. And so this here is the volume of the gas that was occupying that cell at 100 degrees C that then had reliquefied. And you can usually see that quantity because there's about 1 gram left, so you'll be able to see that sample that remains in the cell. So if I do 112.46 minus 111.34, that's 1.12 gram that remains. That remained as a gas in the container at 100 degrees C. So at 100 degrees C, at the boiling point of water, all of this mass was present as a gas inside of that vessel. And so if you take this equation here, PV is equal to M over molar mass times RT, and then you say, I know the temperature that that sample was at 100 degrees C. So that's at 373 Kelvin. I know the pressure it was at atmospheric pressure, whatever the atmospheric pressure was. So the atmospheric pressure was measured with probably a barometer that day, so 771.5 millimeters of mercury. So the total atmospheric pressure is the pressure inside of that container. So whatever atmospheric pressure is for the day is the pressure that gas would have had inside the container. We know the volume, that's the 355.3 milliliters. And then we know how much mass there was. This is the 1.12. And then the molar mass is the quantity we don't know that we can solve for. So this is a technique that you can do in the lab to determine the molar mass of a sample. So if we do a little rearranging, our molar mass will be equal to MRT divided by PV. So I take mass of the sample, 1.12 gram, times 0.08206 liter atmosphere mole Kelvin, and then multiply that by the temperature. So that the key is that the sample is a gas in the boiling water bath, and the boiling water bath's at 373 Kelvin. So that's why the temperature of our gas here is 373 Kelvin. And then the pressure it was at, 771.5 millimeters of mercury. But I need to convert that to ATM. So 760 exact millimeters of mercury and 1 ATM. You could look up a different gas constant, but remember, you won't have that on the test. So on the test, you'll just have the liter ATM per mole Kelvin and the conversion to ATM available. And then multiply by the volume. Of course, we have to go to liters, so that's 0.3553 liters. But one of the keys is that this is an experimental method that we can use to determine the molar mass of a sample. So there's not a lot of experiments that are, at least this fundamental that we can do that furnish something like a molar mass. So 1.12 times 0.08206 times 373 divide by 771.5 divided by 760, and then times 0.3553. I screwed something up. Here, let's do this. I was even thinking as I was doing the problem that this step here, we might want to do that on the side so we're not in the middle of a math step. So let me do that. 771.5 divided by 760. That's 1.015 ATM. Okay, so let's do this again. 1.12 times 0.08206 times 373 divide by parentheses 1.015 times 0.3553. And so I get 95.06 grams per mole. And let's look at the units real quick to make sure that's what we get. So Kelvin cancels. Liter divided by liter cancels. ATM divided into ATM cancels. And we're left with grams, and we're left with moles not canceling. So everything else had canceled but grams per mole. And so the molar mass of the sample was 95.06 grams per mole. So this is a technique, I think you'll get a chance to do it. That's what they do in the lab, right? Still something like that, or no? Not anymore? We used to do this. We should do this still. It's a fun experiment. It doesn't always work right. The data you get doesn't always match what you expect, and the reason why is sometimes you don't completely vaporize the sample. So a lot of times we really didn't totally vaporize the sample. So that's, and then sometimes the sample cools and air gets back in, and then we think it's all the gas sample. So sometimes it doesn't work well. But it's at least an experimental technique we can use to determine the molar mass of a gas sample. There's a problem I can think on one of the daily quizzes that kind of is a problem just like that. And it's just like the problem will tell you almost always how much sample is initially in the bulb and then how much after vaporizing. The key is after you vaporize all the sample, that's how much was left in the container. That's why you know that was the mass of the gas after it was totally vaporized and occupying that container. Now let's talk about the behavior of gases. So how do gases behave? The kinetic molecular theory of gases tries to explain why gases behave the way they do. It has some postulates like gases are in random motion. So if you imagine a gas sample, the particles are always in motion. The particles aren't standing still. Even if you picture a liquid or solid sample, those atoms are still in motion. Unless you get all the way down to 0 Kelvin, which is theoretically not even attainable. But if you got to 0 Kelvin, then motion would cease. So if you're at any temperature, atoms are always moving, even in a solid sample, even in a liquid, certainly in a gas sample. You can imagine a gas sample is going to have a lot faster motion on average compared to a liquid sample, compared to a solid sample, of course. And so the particles are in random motion. The particles occupy a negligible portion of the volume of the container. This is one of the things we're talking briefly about with the ideal gas law. One of the things that makes an ideal gas is that the particles of the gas don't take up most of the container. So we have most of the container available as empty space, so the particle volume itself is a negligible portion of the volume of the container, and that there are no attractive forces. So the attractive forces are negligible. So the particles aren't sticking together. They're maybe bouncing off each other like billiard balls, but they're never actually experiencing molecular attraction. The constant average kinetic energy can be described for the sample, meaning that the sample has a certain amount of energy that's a constant, and we're not creating or destroying energy by collisions. So if we have a fast particle collide into a slow particle, the slow particle may become the faster particle, and the faster particle slow down, but through the collision, we have to have the conservation of energy. And so the entire sample's at a constant average energy. Unless we change the temperature, we're not changing the average kinetic energy of our gas mixture. So the average kinetic energy itself is proportional to temperature. So if you increase the temperature, you increase the average kinetic energy. I think the one equation from physics that almost everybody will remember forever is 1/2 mv squared. So kinetic energy is 1/2 mv squared. So if you increase the average kinetic energy, what you're doing is by increasing the temperature. So you increase the temperature, you increase the average kinetic energy, then you make the particles move faster. So temperature is just a way to understand a relationship to how fast those particles are moving. And then molecules can collide with each other, but like we're talking about, energy has to be conserved through collisions. And then also through collisions, the particles aren't like sticking together. They might bump into each other, but it's just like a billiard ball type picture for how the gas particles are behaving. And so we can think of how different aspects of the gas laws can be understood through the kinetic molecular theory of gases. And so if you imagine a gas is compressed at constant temperature, so what that means is we have some sort of a piston that we can move downward and decrease and sort of compress that gas. So as we're decreasing the volume, we had talked earlier that we're increasing the pressure. And so let's think about what it means to increase the pressure. If you think of what pressure means, remember how pressure was a force exerted by a square area. If you can think of the pressure due to the particles hitting the walls of the container, if we have particles inside this container in random motion, that as we decrease the volume, they're going to hit the walls more frequently. So you increase the frequency of collisions with the walls of the container. But when you press down on the container, do you think you've changed the velocity of the particles? As I press downward, and then the particles, and I'm not talking about the actual pressing and changing the position of the particles, but once the particles come to rest and they're moving around the container, has their average speed increase or decrease or change at all by the process? And so when I'm thinking about the frequency of collisions with the walls of the container, those are indeed increasing. Like that's what happens when you decrease the volume, is you make there be more collisions. That's putting more force per unit area on the walls of the container. That's why the pressure increases. So statement 1 would explain why the pressure increases as we decrease the volume. But then what would it mean for the average velocity of the particles to increase? You know, like this is something like on a test, I know we asked this question, we would think, we're not actually talking about the process of pressing downward here and decreasing the volume. we're saying press downward and then look at the velocities once the particles have settled downward. They're going to be traveling at the exact same speed because average velocity is proportional to temperature, and we didn't change the temperature. So to make those particles move faster on average, we're going to have to increase the temperature. So by decreasing the volume, we're not increasing the pressure because the particles are moving faster now. We're increasing the pressure because there's more particles hitting the walls of the container on average at any moment in time. So the frequency of collisions is what increases, not the actual speed of the particles. So only statement 1 here is going on. So by changing a property at constant temperature, we cannot change the average velocity of the particles. If we want to change the average velocity of the particles, we have to increase or decrease temperature. If you increase the temperature, then the particle velocity will increase on average for our particles. If you decrease the temperature, then we can decrease the average velocity of the particles. So then that leads into, well, how fast are these particles moving? And do they have a narrow velocity range or a wide velocity range? And as you might imagine, if you have, imagine like in Avogadro's picture, imagine having 22.4 liters of a gas, so that'd be a pretty big volume, and that's a mole of a gas at STP at 1 atm at 273 Kelvin. And so a gas is occupying a pretty big volume, that's 1 mole of a gas. And so that would be 6.022 times 10 to the 23 particles inside of that container. Now you can imagine it would be kind of crazy if they all had the same velocity, right? So if every particle had exactly the same velocity, that would be pretty hard to imagine because these particles are all bouncing into each other, some fast, some slow. On average, we can understand the velocity perhaps, but there should be a wide range of velocities. So at 0 degrees C, the blue curve is trying to show that we have a wide range of velocities for our gas sample. And if we compare that to 100 degrees C, what we would do at 100 is we would just shift that average higher. So we'd just be shifting the curve higher. We'd have more particles that are able to achieve a faster velocity on average, and we'd have fewer particles traveling slower within that gas mixture. But on average, like we can think then of how do we classify the average? Because if you're looking at this distribution, it's not a perfect parabola. So we actually get 3 different points that we can classify. We have the most probable velocity, that's the maximum point. So the maximum point is our most probable velocity. We have the average, which is the simple computed average of all the particles. You add up all the particles, you divide by the simple average, that's your average velocity. And then you have something called the root mean square velocity, which is hard to comprehend what this means, but this is just the velocity at which it's the velocity that corresponds to the average kinetic energy that the sample has. And so the average kinetic energy applied to the sample. So if you knew what the average kinetic energy was, that you're just relating this to the 1/2 mv squared. And so the root mean squared is the speed of the molecules whose kinetic energy is equal to the average or mean kinetic energy of all the molecules in the sample. And so the 3 just are not overlaid on the same point because we have more particles traveling faster. So we have like more particles on the faster side, fewer particles on the slower side. So if you notice here, this range here is smaller than this range here. So we call this like a Boltzmann distribution, wherever you get this kind of like tailing curve. You get the tailing curve because it's more possible for the particles to have that faster velocity than the slower velocity. So again, most probable is the top of the point at the top of the curve. The average is the average speed of the molecules, the simple computed average, and the root mean squared is that one associated with the average kinetic energy. Now, these have values that you can calculate, or this is comparing the same picture. I don't know why I have this in here twice. This is basically the same slide as before. But there's ways to calculate the most probable and the root mean square velocity off of a equation. So the root mean square velocity ends up being equal to, so the VRMS is equal to the square root of 3RT divided by the molar mass of the gas. So we can calculate the root mean square velocity by knowing the ideal gas constant, the temperature, and the molar mass of the gas sample. We'll have to think about units though. And then the most probable velocity is a little bit lower. This one is 2 times RT divided by the molar mass. And the average, I don't know how to calculate the average. But these two we can calculate just off of RT and the molar mass. Now what these are going to lead us into is thinking that R, or if we even think about velocity, we want this in meters per second. Like if we want a velocity, we want it in an SI unit. And so if we want these speeds to come out with an SI unit, we're going to have to look for a different unit of R. We're going to have to look for a gas constant to be 1 in SI units, not in like a non-SI unit of pressure like ATM. So we're going to have to look at R, we're going to have to change it to a different value that's in SI units, and then we're going to have to think about what units we want the molar mass to be in. But let's look at solving these problems when we get back on Wednesday. So enjoy the weekend. Hopefully we get to see the eclipse, and we will power that through the rest of the semester. All right, guys, have a good one.